Basically, operons are a series of genes controlled by a promoter site. There is a regulator whose job it is to make a repressor protein. There is a promoter, which is where the RNA polymerase actually attaches to the operon. And there is an operator, and that operator is going to determine if the polymerase will function, meaning if the polymerase will transcribe. And this is going to be our theme throughout both operons we're going to talk about. If the repressor protein bonds to the operator, means if the repressor can do its job. Repress means to stop from happening. So if the repressor represses, then the polymerase isn't going to be able to transcribe. If polymerase can't transcribe, then we can't have translation, then we can't have proteins. And then after the operon itself, we then have the structural genes. That's what's actually being controlled. In a lot of ways, you can think of an operon like a switch, determining whether to turn the genes on for transcription or to turn the genes off. And more often than not, operons are a prokaryotic control mechanism. Eukaryotes have DNA methylation, histone acetylation. Bacteria tend to use operons. And what we're going to do with the diagram that I gave you is we're going to look at two different examples. One being repressible and one being inducible. Now the first thing you need to understand is that these things don't look like the picture I gave you. It's just an illustration to show you. It's still related. It's got to do with physical shape. If you recall when we talked about steric regulation, allosteric regulation with proteins, changing structure, changing function, this is an example of that. So there is a physical changing of the shape. But, I don't want you going home thinking that, bacteria have operons that look like Legos. It's not really that. And I have learned over the years that sometimes that's the stuff that people focus most on, and they get really depressed when they realize that you really don't look like you don't have little Legos inside you. It's not the point. It's to see the picture of what's going on. So the first example we have is repressible control. Every one of you has experience with repressible control. May have had experience in the last week. Because other than the last couple of days, weren't we in that trend where it was getting cooler? Maybe you even broke down and turned the heat on a couple of those nights that were chilly. If not, within the next couple of weeks, like it or not, the heat will be going on. If you're cold, you turn the heat on. You ask for heat. Now, does that mean when your house gets too hot, you open all the windows to cool down? No. Because the very thing you're asking for, heat, is what causes the heat to shut off, right? When it gets warm enough, the heat causes the thermostat to shut down. That's repressible control. The thing you're interested in shuts the system down. Repressible control, that's what we're talking about. And the best example, kind of the classic example we look at, is something called the trip operon. short for the tryptophan operon. And big surprise, the trip operon codes for the production of tryptophan. So, if tryptophan levels are low, in other words, there is not much tryptophan in the cell, so the cell has to make some. When tryptophan levels are low, the repressor doesn't fit into the operator. And you can see that in the diagram. One time I wish I had dual screens. This repressor isn't going to fit in that operator, is it? So when tryptophan levels are low, the repressor doesn't fit. If the repressor can't repress, doesn't that mean we're going to make protein? Because the polymerase functions, it goes right by the operator, moves right on down, transcribes the genes for tryptophan. We're making tryptophan. Well, sooner or later, the cell's going to have enough tryptophan. It's making what it needs. Eventually, it has enough. And again, we're talking about systems tending not to be wasteful, so you don't want to make tryptophan you don't need. So when the tryptophan levels get high, cells making tryptophan, we get a lot of tryptophan in the cell. The tryptophan itself is going to bind to the repressor. When the tryptophan binds to that repressor, it's going to change the shape of that repressor protein. Back to that allosteric regulation we were talking about. It changes the shape of the repressor protein. Now the repressor fits into the operator. Well, if the repressor can repress, we're going to stop making proteins, aren't we? Because polymerase is going to be blocked. Polymerase can't go through, transcription can't happen. Transcription can't happen, translation can't happen. So the end result is we stop making the enzymes to make tryptophan. And that in and of itself is a repressible system because of the fact that this is all about making enzymes to make tryptophan. Tryptophan itself is what shuts the system down. That's why we call it repressible. The product you're making turns the system off. Now that cell is going to use up that tryptophan for varieties of things, making proteins, etc. Eventually, when the tryptophan levels get low again, then simple diffusion is going to cause that tryptophan to come off that repressor. I can show you that picture. Is under normal circumstances, for lack of a better word, regulated